Hey, Calculus. We are beginning chapter 10, and so we are moving on to what is our last big category of calculus. So we started with limits, and then we studied derivatives and how those relate to limits. Then we talked about integrals and how those relate to derivatives. And now we are moving on to our last topic, which is sequences and series. And these will relate to everything. We will use limits, we will use derivatives, and we will use integrals in this unit. This is a long chapter, so it's going to take us about 3 weeks to cover the content of chapter 10. So today we're going to be talking about sequences. In general, a sequence is just a list of numbers separated by commas where there's some sort of a pattern to the list of numbers. They can be represented on a number line. So on that top one, the pattern or the rule is that a sub n is how we read that, is the square root of n. So that means as we count up by integers, so when n is 1, we plug in 1, and then we plug in 2, and then we plug in 3, and then we plug in 4, and then we plug in 5, etc. We can then plot those either on a number line or on an XY axis where we have our x-axis representing the n value we plugged in and our y-axis representing the a sub n, or what we get then for that term of the sequence. Likewise, on the next one, we're doing 1 divided by n. It's important to pay attention to the labels by those dots, because on the number line, we want to see that those values of the sequence then are actually getting closer to 0. That's probably a little bit easier to see on the two-dimensional graph there, the XY axis graph. And then on that last one, we see this flipping happen where as we move from term to term, we get negative answers and positive answers back and forth. That happens when we have a -1 raised to a power. That's going to be a little trick for us. When we need to come up with a sequence where we see the sign flipping back and forth, we're going to use a -1 raised to a power. And we see those flipping back and forth, but still as we look at that graph, each point is getting closer than the last one to that 0 axis line. So the question then with a sequence is, are they becoming something? Are the list of numbers, are they settling in on some values? So in these, we would say in that first one, it doesn't really look like it. It looks like those dots are just increasing as they move across the graph. But on the second one, it does look like those graphs are settling in and trying to become, or those dots are settling in and trying to have a value of 0, the bigger for the values of n. And then in that last one, again, even though they're bouncing back and forth, it does look like they are still trying to settle in on a value of 0 for the terms of that sequence. So then we think about this idea of limits. And earlier this year, we learned about that fancy delta epsilon definition of a limit, and we could apply that here and say, can we put a neighborhood around these that after some point, all of the points are going to stay within that tiny neighborhood? And if so, we're going to say that the sequence converges, that it's settling in on some number. And if not, we're going to say that that sequence diverges. With sequences, we're going to be looking then at taking the limits as n goes out to infinity to determine if they converge or diverge. And we can add, subtract, multiply by a constant, multiply by each other, and divide sequence values to determine their limits. In this one, it looks like we have two sequences, C sub n and B sub n, where we know for sure those are both settling in on some limiting value L. We're not really sure what B is doing, but then we're going to talk about them being squeezed or sandwiched together there. So perhaps we could find two sequences that we do know what they do, and that can help us figure out a sequence that we don't know what it does. And that is that sandwich theorem. So let's see, for our purposes, for our assignments, these may be helpful to you in the homework, some common limits, but these are all limits that you actually know how to take as well by thinking about L'Hopital's rule for the most part, except for maybe 5 and 6. So 5 is a really special limit for us there, that is actually the function that defines the value e. So as we plug in bigger and bigger and bigger values for n, that is actually going to become e to the x. So if x was actually replaced with a 1 in that formula there, then we would just get the value of e, Euler's number. And then on 6, don't really know how to take L'Hopital's rule, take derivatives with factorials, but if n is a factorial, we are going to say that in general we can assume that factorial functions are going to grow faster than even exponential functions, which we have talked about as being a very fast growing function. So the denominator there is bigger, and that's what gives us the limit value of 0. So let's see. All right, so let's do some examples of what you're going to see in your assignment here. First type of problem we're going to see is going to give us a sequence rule, an a sub n definition, where n is our counting number starting usually at 1. We could start at 0, but you'll just look at your instructions on the question for that. Typically, we are going to start them at 1, and then we can find what are the values of this sequence. So if we plug in 1, we're just going to replace all of the 1s with, or all the n's rather, with a 1. So we get 5 over negative 1. So our first value of this sequence then is negative 5. Then we could plug in a 2 to our rule here. So that's a minus 3. And so we get 8 plus 1 is 9, and 4 minus 3 is 1. So our second term is 9. And then we plug in a 3, and we could say then our third term is 12 plus 1 is 13 over 6 minus 3 is 3, and that's not really going to reduce at all, so we'll just leave it right there. We could turn it into a mixed number if we wanted to, but that's harder to type in for our answers. So we would just leave it right there. Now, a question with these is, are those values beginning to settle in? Are they becoming something or not? So there's a pattern to them, but are they converging to some certain value? To tell that, we're going to take a limit as n goes to infinity. So if we do the limit as n goes to infinity here of this sequence, well, if we plugged in, we can't really plug in infinity, but if we plug in huge numbers, we're going to have really huge over really huge. So that's where we can think about using L'Hopital's rule. Then if we apply L'Hopital's rule to this and take a derivative of the top, we just get 4, and a derivative of the bottom is 2, so we get an answer of 2. That means these values are actually converging. They are settling in to become 2. So we only found the first 3 terms, and none of those answers were very close to 2. But if we kept finding more and more and more terms of this, what we would find is that those terms are getting closer and closer to settling in on becoming just 2 every single time. We can also define a sequence what is called recursively. If we define a sequence recursively, you're going to be given at least one starting value, sometimes more than that, and then you're going to be given a rule for how the next term relates to what that last term was. So this is what a recursive definition looks like. Our first answer to this sequence, our first term in this sequence, is 1. They give us that. Then after that, what we want to do is say that a sub 1 plus 1, which would be a sub 2, is equal to a sub n, where that's our last term, because I'm plugging in this case, n equals 1, replacing the n with a 1 there, so that would be our a sub 1 term, which would be 1, plus 1/2 to the power of 1. So 1 plus 1/2 is 1 1/2, and I'm just going to leave it as that mixed number. I could change it to an improper fraction if I wanted to. Then if I plug in a 2, a sub 2 plus 1, well, that's really like a sub 3. Sorry, some of my a's are kind of looking like 9s. They are a's. It's just hard to write on this iPad. For that, we take our last answer, So that would be 1n1/2. That's that a sub n. That means what that last answer was. And then we are going to add to that 1/2 now to the power of 2. So that's 1.5 plus a fourth. So that would be 1 3/4. And then we could continue on with that pattern. We'll just go one more. Unfortunately, I think on your homework, you get to go to like 9 of them. So you're going to get to work with some really tiny fractions there, but just go ahead and use your calculator as necessary here. But for our a sub 4 term, we're going to take that last answer and we're going to plug in a 3 for, oops, I said a over here. That's supposed to be an n. N is 3. So that's plus 1/8. And so if I add 1/8, I'm going to get 1 7/8 there, 3/4, and get a common denominator of 8s. That'd be 6/8 plus the 1/8 would make 7/8. And then we could think about, well, is that settling in on anything? It does certainly seem to be settling in on something, right? As n is going to infinity, that 1/2 fraction is not accumulating very much more each time. So those terms definitely do seem to be settling in on something. It seems like this series will be convergent. We're probably never going to pass a value of 2, right? They're probably settling in on the value of 2. In some of your problems in your assignment, you're going to be asked to find the rule that defines the sequence of terms. So sometimes you'll be given that sequence of terms, and sometimes you'll need to come up with the rule. Sometimes you'll be given the rule and you come up with a sequence. So here's our list of terms, and we want to say, how can I write a rule that I can plug in n and get this sequence of numbers? Now, when you do this, you're going to be not coming up with a recursive rule, but rather what we call the explicit rule, where it's only based on n, the term's position in line. So when we do that, we're typically going to begin with 1. Again, we can begin really with any value we want. So pay attention to the problems. I do believe most of your homework problems ask you to begin at 1. So what we want to do is say, how can I create these terms by plugging in 1 and plugging in 2 and plugging in 3 and plugging in 4 and plugging in 5. So we want to look at what's happening as we move from term to term to term. It looks like we are multiplying here by a -2. So if I'm multiplying by a -2, I could say this is -2 to some power. But I'm actually going to go ahead and split that up, and I'm going to deal with the negative and the 2 separately. That negative flipping back and forth, I'm going to take care of as a -1 to a power. So if -1 is being raised to the first power, then that would create a negative answer. So if I want the 1 to be a positive, I'm going to have to do like an n plus 1 there. If I just use an n, that would make my first term in line be negative. So I want to move that over 1 spot and make negative happen for the second term in line. Now for the 2's, if I'm raising 2 to the first power, I'd get 2, but that's over too far, but the other way. So I'm going to put that to our n minus 1 here. Then if I plugged in 1, I'd get 0, and 2 to the 0 is 1. If I plug in 2, I'd get 1, and that would give me the 2 that I need, and so on and so forth there. Now in this sequence, it actually would work to combine those together and have them be both to the n minus 1 power. This is the same. This would give us the same value if we did a -2 to the power of n minus 1. But I wanted to show how to deal with that positive-negative flip-flop separate from the powers, because positive-negative flip-flops can happen even in non-exponential base sequences. So let's look at another list of numbers and come up with a pattern there. So we've got, let's say, we've got 1/4, 4/7, 9/10, 16/13, and 25/16, etc. What rule can we come up with here? Now, often in fractions, it may be helpful to consider the numerator separate than the denominator and look for separate patterns there. So as we look at those numbers on top, hopefully they shout out to you what they are. 1, 4, 9, 16, 25 hopefully is a set of numbers that we are familiar with as being our squares. So again, we're going to begin this with n as 1 and count from there. So those are our squares. And so we're going to say that is n squared, and it works out to start with 1 and then 2 and then 3 would give us the right values on top. So we don't need to adjust n by adding or subtracting anything from it. On the bottom, 4, 7, 10, 13, 16. We want to look at what change is happening here as we move from term to term to term. Each time we are adding 3. We want to think about what kind of math is going to make us add 3 every time. The most common student mistake is for students to want to do something like n plus 3. We're adding 3 every time. But when we think back to the way that we defined our math functions in elementary school, we think about what is adding over and over and over. If I have 3 plus 3 plus 3 plus 3 plus 3 plus 3 again, we learned that repeated addition is actually multiplication. So this rule is going to be a 3 times n. But if I plug in 1, that gives me 3, and I'm supposed to have 4. So I'm going to go ahead and add 1 to that and see if that continues to work. Then if I plug in 2, that would give me 6 plus 1 is 7. If I plug in 3, that would give me 9 plus 1 is 10, and that does seem to work to create my terms. So that is our a sub n rule. So looking for those patterns there, look for, are we multiplying by the same thing? Are we adding or subtracting the same thing? Do we have special sets of numbers that we know, like our perfect squares? Now we're going to go back to that idea of convergent and divergent. We want to say, is the sequence going to converge or is it going to diverge? And if it converges, what is it going to converge to? So for this one, let's say we're going to take our then limit. As we think about convergence, we're thinking about as we're plugging in bigger and bigger and bigger values of n way down the line, what are these terms becoming? So as n goes to infinity, raising a half times 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 a half is going to become 0. Plus the 4 will give us 4. So this is a convergent sequence of terms, and the terms are, in the end, settling down to become a 4. And then one more of these. Let's say that our sequence is 3n to the 4th plus 2n to the 3rd over 4n cubed plus n. All right, so if we, again, are thinking about what are these terms becoming way down the line, we're thinking about what are these terms as n becomes infinitely large. And so as n becomes infinitely large, we are going to get infinity over infinity here. And that's the perfect case for L'Hopital's rule. So we could take a L'Hopital's rule on this. We would need to take L'Hopital's rule 3 times before we would come to a solution on this. Or we can think about, well, earlier this year when we did limits, we talked about how our highest powers kind of win the battle. So if we just look at those highest powers and say that in the end, those other parts, although significant, aren't really going to matter, then this could be reduced to become, in the end, about the same thing as 3n over 4. And if n is becoming infinitely large, then this sequence is going to be divergent. As n becomes infinitely large, so do the terms of this sequence. That's the end of lesson 10.1 about sequences.